This is the systems of linear equations engineering applications example. Here we have an electric circuits example. And systems of linear equations happen all the time for electrical circuits and lots of engineering applications in general. So we'll see a couple of them here. Electrical circuits example, an engineering student is trying to solve a problem, and she's got to figure out the values for I1 and I2, which are values of current measured in amps, and she's correctly arrived at the two linear equations below, probably by using Kirchhoff's current laws or voltage laws, and was able to determine these things. And she needs to solve for I1 and I2, and they're asking us to do it in several different ways, through addition, substitution, matrix algebra, and Cramer's rule. And really for these, like I said, you're going to come up with these a lot. In general, if you're solving by hand, you're going to use one of these two, either addition or substitution. And if you've got a computer that can do it for you, they're going to generally just use the matrix algebra, or they may use some form of Cramer's rule. But just to start out, we're going to solve it using addition. So let's look at that one. We've got a circuits example. We know that 10 I1 plus 4 I2 is equal to 6 volt. Presumably these are resistance values and these are currents, and that's a volt. If you remember some other problems we talked about circuits, V is equal to I times R, so probably these coefficients are resistance values, and we're trying to make sure that the voltage balances out. So we have these two equations. We want to solve it by addition. We should probably go ahead and define these, that I1 and I2 are currents measured in amps. So addition. So the key to addition is first we got to make sure to line them up. Make sure that and I'm going to not include all the significant figures right now, but we have to make sure that everything lines up so that equation 1 and equation 2, all the parts line up. We've got the same variables there. We've lined up the coefficient. We've lined up the right-hand sides. And all these parts work out. And I'm going to call this equation 1 and this one equation 2 so that I can talk about them in this part. So then we must multiply one of the equations such that when we add it to the other, or when one of the variables disappears. And what I mean by that is basically that a variable becomes, the coefficient for one of the variables becomes 0, is how we get it to disappear. So how do we pick that? Well, we want to look for plus or minus 1 coefficients. Plus or minus 2 are usually really easy to work with. Things like 5s and 10s, those are easy to work with. So if we see one of those things, they can generally give us a hint as to which ones to use. In this one, we have a 10, but it doesn't really match well with the other. What we do have here is the other thing we can look for look for coefficients that are a factor of the other. So in this case, I have 4 and 12. Well, 12 is just 3 times 4. So I'm going to take you can choose to do it a different way. You could have chosen to take in this one, multiply it by 2.5, and that sort of thing. So what I'm going to do is multiply. I'm going to zoom out a little bit as we start extending down the page. Multiply equation 2 by -3. And so if I do that, I get -3 times, I'm going to take the full equation, 4i1 plus 12i2 equals 9. I take everything and multiply it by -3. So I get, I'm sorry, I took the wrong equation. I need to take equation 1 and multiply it by -3. That way I get the one to cancel out. 10 and 4 and 6. Sorry. Alright, so -3 times 10 is -30i1 minus 12i2, which is what I was going after, and minus 18 on the right side. Then I can add the other equation. So 4i1 plus 12i2 equals 9. And if I add those two together, I get -26i1. I get 0 times i2, which is what I was going for. And I get -9 here. Okay, so then I can simplify that. This goes away. I've got -26 times I is -9, so then I1 must equal 9 over 26. And again, if I was going for a final answer on that, that would be a terrible way to write things. I guess technically it's -9 over 26, which is the same as 9 over 26. If I was doing a math problem, that would probably be a good place to stop. But we've mentioned several times, in engineering we generally want to get a decimal answer. So I'm going to take the 9 divided by 26 in my calculator, and I get that it's 0.346 amps. Okay? Then once I have that, I can use either equation with my known value. And I'm going to choose, since I've got I1, I'm going to choose equation 1. It doesn't really matter. But to use equation 1, I'm going to say 10 times the 0.346. I do like that 10 is going to be an easy number for me to multiply. Plus 4 times I2 is going to equal 6. And in that case, 4 times I2 is going to equal 6 minus 10. Well, I can just go ahead and do that. Minus the 3.46. So I2 is going to equal 6 minus my answer divided by 4. I2 is 1.413 amps. That doesn't seem right to me. Because I did not multiply by 10 up there. So let's try that again. 6 minus 3.46, and I'm going to use some of the extra decimals that I have up top. There we go. I get 2.5 divided by 4. There we go. 0.635 amps. So just note it back over here so it's easier to keep up with, that I1 was 3.46 and I2 is 0.6. I'm sorry, it's 0.346. I2 is 0.635. A good thing to do once you solve that is to substitute those back into the equations and make the original equations and make sure they work. Since we're going to do this a couple more times, I'm not going to worry about redoing that.